Today I'll devote this session primarily for. Sorry, the slide is visible, right?
Yes, sir.
Yeah. Today I'll devote this session primarily, then continuing what we have been discussing or continuing the portion. We will discuss primarily the midterm questions and answers to some of them where people seem to have some confusion. So that will be the focus of today's session. But I'll just take a couple of minutes to state what we are going to discuss in the portion next. So far, we have restricted our attention to uh, simplistic models which can address bodies which are relatively slender in shape. So what we are now going to look at is, again, it's just getting a feel of how some of the physics associated with blunt bodies can be modeled or rather analyzed. It's not a detailed modeling. We are restricted because we cannot do a detailed modeling without numerical methods. So in an analytical fashion, how they can be looked out will be one of the approaches for that is what is going to be discussed next, which is called as hypersonic equivalence, the method of hypersonic equivalence. The transformation is from similarity analysis, what we have just done, to the equivalence approach. And as I mentioned, the similarity is restricted to slender bodies, whereas hypersonic equivalence is an attempt to extend the approximate analysis to blunt-nosed bodies. Again, blunt-nosed slender bodies. So we should be careful. I'll try to explain that later also with sketches. The nose is blunt, but the body is still slender. So you will have a detached shock, but the slenderness is still retained. Slenderness we have considered all through, that will be retained, but the nose shape will be can be blunt. And this also has several applications in real hypersonic systems for reasons that we will see later. That is why blunt nosed bodies are preferred in some cases. We'll be discussing that when we talk about heat transfer. But then from here, we will be looking at what is meant by the hypersonic equivalence and the approach that is based on the concept of hypersonic equivalence, which will require a little bit of extension of a 2D flow, 2D steady flow to 1D unsteady flow. That is, it's basically striking a balance between a 2D steady flow and a one-dimensional unsteady flow. The argument behind that is what we are going to highlight here. We'll take that up afresh in the next class and take it onwards from there. So today, as I mentioned, we will focus primarily on the questions of midterm quiz, midterm exam, and I'm particularly taking up the questions which where people seem to have, I'm sorry, uh, people seem to have some confusion, and so that we can discuss them, we can clarify, and if I have made a mistake, which I think at least in one instance, so I can correct myself, I can take care of that in the evaluation. And if there are other clarifications required, I can try to provide that also. This is the pattern that I just took from AUMS, the percentage correct answers for Q1, Q2, etc. So on x-axis, you have the title of the histogram is plotted for different questions with the percentage correct answers. Okay. So you can see that there are a few questions for which, so what I am going to discuss today or what we are going to take up here are questions where 80% or below people have got it correctly. 80 and above, I'm just leaving. We can actually, because since most people know it. Otherwise, I mean, I'm not excluding. So if you have anybody, if anybody has doubt about the questions that I'm not going to discuss today, they can get back to me. I can individually explain or I can explain in the next class, etc. So I'm not avoiding them. I'm not excluding them. So if somebody has doubts about, I'm just putting 80 as just a mark so that most people know it, and others, if there are confusion, we can anyway individually discuss it or even in the class. No issue. So for now, I'm just the way that I have put this PPT is I just identified the questions for which less than 80% of people have got correct answer. So we'll discuss them, and if there are further clarifications required, we can try to provide that also. Question 2 of 15, I guess that is, yeah, just above 60 is what the correct answer seems to be, 60%. The question is, calculation of pressure distribution by shock expansion method is, the options are, is independent of angle of attack, always assume symmetry of the flow field, and is applicable in supersonic and hypersonic range, and is independent of Mach number. Anybody has doubt about the correct answer which was given in this?
Sir, I have doubts, sir.
Ah.
Sir, in this answer is applicable for supersonic and hypersonic, sir, but this shock expansion drawback itself is that reflected shock wave, it should not be considered for shock expansion method, sir.
That is right. Yeah, the reflection can impact the accuracy of shock expansion.
So in case of hypersonic, it will travel downstream, sir, but supersonic, it will get impacted, sir. So how it is applicable for supersonic?
Now, it doesn't stop its applicability. Actually, it impacts its accuracy. So it's not a theoretical restriction, because shock expansion is used in supersonic range also. But then, yeah, the accuracy, because particularly in shapes where you have a reflected shock, it can impact the accuracy. That's all. But the theoretical applicability is there for supersonic and hypersonic range as well.
Okay. Sir, in this B wave
that's what. So that's what I'm trying to explain now. I'll try to explain why the others are wrong. Okay. Is independent of angle of attack. I hope it should be obvious, because if there is an angle of attack, then the initial formation itself is going to be different for the two phases. Okay. And always assumes symmetry. That's not correct, because even there is an asymmetry. That is, for example, if there is an angle of attack, there is an asymmetry. Even in that case, we can use the shock expansion method. Only thing we should be careful about where we are taking shock and where we are taking expansion, because the response of the flow will be different on the two sides. So when you have an angle of attack, the flow is going to be asymmetric. And but despite that, the method is still applicable. Okay. C we have discussed already, and obviously it's not independent of Mach number. The method depends on shock calculations and expansion calculations, which are dependent on the Mach number. So for example, the leading edge, the values that we are going to get is certainly dependent on the upstream Mach number. So the calculation procedure is not independent of Mach number. Is that okay? Reasonable? Shall I proceed? Okay. Now question number 3, and let's see. Q3. Yeah, that's close to 80, actually 75, probably around that. Calculation of pressure distribution. I'm sorry, 3. The wave drag. These are actually related. Wave drag is 1. Independent of angle of attack, primarily due to viscous forces, can be present in let's go one by one. The first statement is is dependent on the angle of attack is the first choice, and that's the correct one. Because wave angle is because of the oblique shocks and expansion fans formed, and the formation of them is certainly dependent on the angle of attack. So the first one is correct. We'll see why the others are wrong. Primarily due to viscous forces, certainly not, because in all these analysis we are not considering viscosity at all. And the cause for wave drag is the pressure distribution, which is present even in the absence of, or even if you do not account for viscous forces. So the pressure distribution that occur because of the formation of shocks and expansion fans is what leads to the formation of wave drag, what leads to wave drag, and is not dependent on viscous forces. And certainly cannot be present in subsonic flow because the formation is because of oblique shocks and expansion fans. We know that no such concepts in no such physics in subsonic flow where you can have a expansion fan or a shock. So it cannot be present in subsonic flow even if there is angle of attack. And none of them is not correct because the first one is applicable anyway. Is that okay? Shall I move forward?
Yes, sir.
Yeah. Fourth one. How was that? Q4. 60 and above. Yeah, I think similar to Q2. Just above 60, maybe 65 or close to 70 or something. Anyway, which one was it? 4? Wave drag, again related to wave drag. For a flat plate, non-zero angle of attack in hypersonic flow is independent of the ratio of specific hits is anywhere ruled out because all those calculations for pressure and change in pressure, etc., whether it is expansion or compression, they all invariably have gamma. So nothing is independent of ratio of specific hits. Is independent of the angle of attack if the Mach number is sufficiently high. No, the wave drag, the pressure jumps or the pressure variations that occur is dependent on the Mach number, even if the Mach number is high. The variations of them, upstream, downstream variations, because the wave drag is because of the variations, and they do depend on the Mach number in any range. So the absolute value of wave drag is not independent of Mach number. Cannot be estimated using shocks expansion method is a fairly useful method for estimating wave drag. I use the word estimating. Estimating means getting a rough idea, not accurate prediction. So estimation is fine. So wave drag can be estimated, which means that all the three are not applicable. Which so the none of them is applicable. So the choice D is the correct one. Okay, so if so, if it's fine, I'll just move to the next one. Question 8. That's I guess it's almost 80% has got that, but then it appeared to be slightly just at 80 or maybe slightly lower than that. So I just included that also in this. Possibly it should be very straightforward.
Excuse me, sir.
Please, yeah.
Sir, I have a question.
So,
I have a doubt in the previous question.
This one,
yes,
this one.
This one.
Yeah, please.
Yes,
Yeah, please.
So if it's a flat plate with zero angle of attack, there is no disturbance in how the for it to cause an oblique shock, right? So we can't estimate it using shock expansion method, right?
No, that depends. If you want to say, if you say that it is there is no disturbance, the thickness has to be 0. Say when we say flat plate, we are not actually in the statement of this. We are not saying the thickness is very small.
Okay, great. Okay.
So if you have a thickness, then you are going to have a leading edge. You are going to have a disturbance because of that.
Okay.
What you said is applicable if it's an extremely thin plate and the flow probably doesn't disturb this one, etc. So that's a theoretical consideration. But then when and unless that is specified, we just have to consider a finite plate.
Okay. Yes.
Non-dimensional pressure distribution. Yeah. In fact, this is the observation is based on experimental studies, and we have seen a brief theoretical explanation for that. Non-dimensional pressure, the statement is non-dimensional pressure distribution on blunt bodies become Mach number independent at lower levels of Mach number as compared to slender bodies. This is correct actually, because for blunt bodies like a cylinder transversely placed or a sphere, etc., or any blunt shape, the Mach number independence is observed even at lower levels of Mach number. That is like 4, 4.5, etc. Whereas for real slender bodies, it may be after 5.5, etc. We have reviewed some experimental results on that, which is available in literature. We have shown that here. And the reason for that is said to be because the whole, the pressure distribution, as we see in P2 by P1, etc., is a function of m sine beta, or rather m squared sine squared beta. So that beta value is playing the difference here. Since you have a blunt, when you have a blunt body, the wave angle is high, so sine squared beta will be high, which means that the approximation of that factor being high, that is m squared sine squared beta being high, is satisfied earlier in the case of blunt bodies. And that's the reason why it's observed that in their case, in the case of blunt bodies, the independence of Mach number on, or independence of pressure distribution of Mach number is observed earlier than in the case of slender bodies. Okay, so that's it's an experimentally verified conclusion. So which basically means that the statement here is true. So true is the correct answer. Which of the following is not true for hypersonic flow field? I'll just go back. 10. Yeah, just below 80. So we'll just see that. Which of the following is not true for hypersonic flow field? Shock formation results in dissipation of kinetic energy to thermal energy is correct, because any shock formation is a dissipation of energy. So that if there is a transfer of energy to the object, then it's basically a transformation from kinetic energy to thermal energy. The flow is losing its energy in terms of kinetic, the velocity, but the temperature increases, and when there is a temperature difference or gradient with an approaching body, then there is heat transfer. So that's basically a transfer of thermal energy. Even within the flow, the internal energy increases, the temperature increases. So it is the statement A is correct. So that's not the choice. Blunt nose results in detached shock waves is very obvious. It's not. It is true. So that's not the correct one also. Wave angle of oblique shock is typically higher than that in SOPA. I'll come to that. Molecular vibration becomes predominant at higher temperatures. As we know, when say at standard atmospheric operating conditions, etc., you don't have, I mean, they are not significant in terms of the contribution to the overall energy. But whereas, say 800 Kelvin onwards, etc., you have higher contribution or higher significance for the molecular vibrations in gases. So at higher temperatures, they become prominent. That is correct also. Whereas option C says wave angle of oblique shock is typically higher than that in supersonic range for a given flow. We know that for a given deflection angle, when theta is specified, the value of beta, the wave angle, decreases when there is increase in Mach number. So which means that in Mach number, that this approximation or this observation we have used in several times, including similarity, the formulation for similarity, and also the calculation for hypersonic limits, etc. So it's a constantly observed or constantly used observation that beta will be, for a given theta, beta will be smaller for higher values of Mach number. So, but the statement is contrary, that is, which says that wave angle is higher for supersonic range, which is not correct. I'm sorry, higher than for hypersonic, it is lower. The statement is it is higher for hypersonic, which is not correct. Okay. So that's a correct statement here. The correct choice here. It's a wrong statement, so that's a correct statement. Now 11. Yeah, here is what I think I have made a mistake. I'm sorry for that. As per Newtonian theory, what did most of you get, by the way, here? The CD value, sorry, the lift to drag ratio, CL, the CL by CD value. Anybody does remember that? Or
1.73.
0.73.
1.73. Yeah, that's what I confirmed later, because since I saw that most people have got wrong, then I was almost sure that I made a mistake. So I went to this is how it is. Q11. I guess only very few people, 3-4 people have opted that. I mean, their answer happens to be in what I have given, but it's wrong actually. I apologize for that. I'll remove this from the evaluation. So this one will not be considered for. So sorry for that. And what you said is correct. It's basically it comes out to be cot alpha, so which comes out to something like 1 point. Guess it is square root of 3 or something like that. It's basically 1.7 around that. Sorry for the mistake in the answer key for that question. Is that all? The last one also, that one, let me see, 15. Yeah, for some reason, I guess it's close to 50%, or just above 50. You got it correctly. Let's see if there is any ambiguity in the statement. As the flow Mach number approaches infinity, value, density of, so please make sure, please keep in mind that what we are asking here is the value of density, which is rho. Which is rho. Whereas what becomes independent of everything is rho2 by rho1, which is not the absolute value of density, which is the ratio of density to the free stream value, right? That's what we see as gamma plus 1 by gamma, which is gamma minus 1, which is about, which tends to be around 6 as Mach number tends to infinity. So it's this is an important point. That's why I wanted to ask this question, because in many of these things where we state about being independent of Mach number, etc., they are the non-dimensional parameters. Say all the limiting values that we calculate, etc., are for the non-dimensionalized. That is for the ratios. They are not for the absolute values. So if Mach number is increasing, density does vary after the shock. Density varies, but what remains constant, or what tends to remain constant at high hypersonic range, is the ratio of density to the free stream density. So rho2 by rho infinity. Okay, so that's this one here. Whereas statement is the value of density of air after the shock tends to be constant, which is not correct. So this one is wrong. So the statement is false. So false is the correct choice. Is that okay? Okay. So if there is, anything else we have to discuss, we can discuss about it now. Any other question or any other confusion in the question paper, or anything? Say like I made a mistake, etc. No. Okay. So this is all that I wanted to do today, and we will move on to the next portion in the next class. So if you don't have any further questions or comments, we'll stop here today, and we'll meet again in the next class. As I said, I'm still a lot of other meetings, and a lot of time is going to other some urgent meetings, etc. So that's the reason I'm not able to finish the Breathing Engines Viva yet. I will certainly finish it this week. Next week I'll put, so by Monday I'll put the schedule for Viva for hypersonic flow, and we'll finish it as early as possible, hopefully in the first half of the next week. Okay, so that's a plan that I have. So unless you have any major conflict, please we will follow that. Okay. Okay, then. Thank you. Thanks to all of you. Bye. We'll stop here.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.